So we now talk about Bitcoin transactions. So what variations exist? Yeah. So we now go a little bit more deeper to talk also about these conditions we have. Yeah. I think this is repetition because it was meant to be at the beginning of the session. So therefore we can skip this. I did this already. And so therefore the network which we are producing is depicted here. Yeah, we focused on this single transaction, but this single transaction obviously gets somewhere its transaction input. And the only way to get transaction input is from transaction output of another transaction. And there are some mining transactions, and the mining transactions don't have an input and produce an output. Yeah, so therefore the way money is created is through mining, and mining produces more or less, if you solve the puzzle, you get money in reward, and this money is more or less this money which is here. So therefore, that's more or less where money comes from, and otherwise money only flows through the net in this transaction web, and it's an acyclic graph, obviously, and so therefore you now have inputs which depend on other outputs, and you have outputs which will be the future input. And these things which are not spent yet, yeah, this output is spent already, and this is an unspent transaction output. Yeah, an unspent transaction output is abbreviated UTXO, unspent transaction output. Yeah, this is the block here with bold with the filled line, and the spent transaction output it has a dotted line around it. Yeah, because and the amount spent here, or the amount what is transferred here, is the amount available here. Okay. So, and now it's the idea of this transaction perspective. So if you now look at the transaction representation in memory, maybe you can even do it here. If you go to a website where you can ask the system to show you the transaction, they would create this such an output as a JSON file. Yeah, it would say, okay, there's several fields, and there's a list of inputs and a list of outputs. Yeah, that's more or less how it's technically represented. We do it visually, yeah, that you more or less have a mental model of it, and you don't have to read JSON files. So therefore, a transaction is this block. It has an in counter, which says how many input variables exist. It's the number n here. N is the in counter. And you have an out counter, which is the number of outputs you have. Yeah, transaction output 1, 2, m. So that would be m. Then you have a version stamp in this transaction, which more or less, again, if you write persistent data structures, it's my mantra as a database professor. Whenever you write something to files or to databases, add a version number if your software changes, so that you know this transaction has created by a certain version of the protocol. Yeah, imagine now in the future that we will have this happens several times, that there are new software versions of the Bitcoin clients, and they likely want to add new features to the Bitcoin. Yeah, and that happened in the past. Then you would always write each client which produces such a block would add the software version number with which this block has been created, so that more or less blocks in the last 10 years have been created, or you now have a new version which has new features. And therefore, in the validation, you can then look at the software version, and then you run a validation algorithm which fits the software version valid at that time. Yeah, so therefore, you have this version information which analyzes the protocol that has been used for this creation. You also have a timestamp, which is nice, that you also can see when this transaction has been submitted. Okay, what else should I just say? Genau. So all inputs reference existing unspent output. Yeah, so therefore each transaction, yeah, so each of these blocks contains the following information. It contains a previous transaction hash. Yeah, it has a pointer to the previous transaction. And as you know, pointers in these systems are hash pointer. And therefore, in order to reference this transaction output, you need the hash value of that one. Yeah, so you reference this one. Then you have the previous transaction output index. In order to reference tricks out one, you would reference to the hash value of this whole transaction, and then to the index of the transaction output. Yeah, so the second one would be the transaction output index here. And that would be the typical connection what you have. And also, if you now go to the right-hand side, and I will talk later about the scripts, the basic protocol would say if I want to spend money, if I look at the transaction output, it contains first the information, how much money do I want to spend? Because that's essentially the core idea here. I want to spend to this party so much money, to the other party so much money. I split the money, so therefore this money is written here. It contains the value in Satoshi. In Satoshi is 10 to the power of minus 8 bitcoins. Now it's a very small, tiny fragment of bitcoins, which is the transaction output. Okay, so what you also want to make sure is that you now want to have the signatures somehow protected, yeah? So that you not only want to say, where does the money come from? So therefore I refer now to this and to this. There I could see how much money goes in here, that's written here. And I also specify how much money goes out. But now I also want to talk about my rights. Yeah? Am I allowed to do this? Yeah? And that's the basic idea, that you now want to play games in Bitcoin. What are the rights that you can transfer money? And the minimum requirement that you would have is people that spend money can only spend money they own themselves. Yeah? So therefore the basic rule would be, if you want to spend money, you have to sign this with your private key. Yeah? So therefore that's the basic idea. And now we want to provide additional code which says, okay, maybe there are conditions for somebody who wants to spend your money. Yeah, so that you say, okay, I give you this money, but before you do this, you have to do something for me. Yeah, so it's like you can now do two things. You can define preconditions or additional conditions for people which want to spend your money. Yeah, that's the idea here. And that you say you get the money if you do the following. For example, show your identity. Or you can do the following if two people show you their identity. Or you can do this if the amount is, I don't know. Yeah? So you could now imagine having conditions which are tied to the receiver, more or less. Yeah? Another thing could be that you have to do, and since you can now do this for your parties to make conditions, you also have to satisfy conditions here. So therefore it's also necessary for you not to only say, I want to get the money, but you have to also give additional information to the previous party where you get the money from. Yeah? So therefore here you essentially say, there's a function, there's a condition, a predicate you have to fulfill. And in order to fulfill the predicate, you have to give this function some input parameters. So therefore, that's a constraint you give to the parties that want to spend the money. And vice versa, if you want to now access this money, maybe it can also be attached with a condition. So therefore, you not only say, I want to use that money, and it's me, but you also may have to provide additional information here, which is required by them. Yeah? And this is the idea why both of these parts contain a script, a field which contains a script in a programming language, a mini tiny programming language which comes with Bitcoin. Yeah? So both of them contain these scripts. And the one script is meant to define constraints, and the other script is meant to provide information for the constraints. Yeah? And in order to show, exactly, and therefore essentially the names for these scripts are called script SIG and script pub key, because they historically, the typical reason for having this script is to provide a public key, and this is more or less a condition script. Yeah? So therefore these are the two names of these scripts. Okay, yeah, so therefore these are the things here. And obviously now through this network, each coin more or less has a history. Yeah? So for example, this coin comes from these two coins here, these coins come from these coins here, etc. Yeah? So therefore you more or less can see where the money comes from. Obviously, as you see, since you have multiple inputs and multiple outputs, it's not really one-to-one mapping where the money comes from, yeah? But more or less you can trace the money flows in total. Okay, as I said, this visual this visual presentation is also then implemented in the system. And if you look at the debugger, essentially, then you will see what are now all this information that are stored. Yeah, you have the version of the protocol, you have a log time, you have a size of the whole thing, you have hash values of this transaction, which can be used as a hash pointer to this transaction. And then you have the list of the inputs here, and each input has a previous output, yeah, which is again the hash pointer to the previous input, and the index here the index 0. The second output, the second input would be a reference to a previous output with this hash value and an index, and then it has an additional script, which is a very long thing, which is a piece of code which will be executed and we talk about this later. The output, in this case, is only a single value, which is now this Satoshi amount of money here, which talks about how much money should be transferred, and then it contains a public key script, and the public key script now is written here not as a binary code, but it's written with some opcodes. It's something like machine code. You know, if you have memory addresses, you can either say it contains data, like here it contains a hash value, or it contains code. And in this case, the system knows it's code, and since it's code, it displays this. The debugger displays this information as opcodes, yeah, with some values. Okay, so that's, I think, the important point. I also mentioned that now the amount of money taken from the sources may be larger than the amount of money going to the output, and this is then the transaction fee, which is later captured on the consensus protocol. Okay, so therefore, well, we have some interesting feature that the code that you're writing here needs to be executed by the miners. Yeah? So therefore, in order to execute these codes, the miners have to have an interpreter which takes these opcodes and interprets these opcodes. Yeah, so therefore, if you look at the source code of the transaction validation code, this transaction validation code is, except these two red lines, a very deterministic piece of code. Yeah, it takes some data from the transaction, computes something, it has all fixed rules, it's not an extensible system, it has a fixed semantics, yeah, except these two red lines. In order to add this flexibility of executing arbitrary conditions, they allow now, they do essentially here this verification of the public key by evaluating now this condition with the parameters supplied by the user. Yeah, that's more or less the condition which has been added to make the Bitcoin programmable, that this is not a fixed protocol, but it's an extensible protocol where the users more or less can add opcodes to their transactions, which are then executed by the clients for having extended validation rules. So that's the main addition, which we'll explain later what is happening here. Otherwise, these are all things you would expect from a system. Yeah, it's all trying to make sure that all values it receives are correct, that no data, money is created out of thin air, that there are no cycles in the network. So all these dependencies are written here. And also which timestamps are set when. This is all written down here in all detail. There's also one sanity check here, that you want to make sure that only certain kinds of transactions can be executed, and there's also an additional condition which only makes sense for you if you know how this scripting language looks like. Okay, so again, if you now zoom in, we see again this scenario, and we know now that these not only contain data values, but also code and data which should match each other. Yeah? So therefore, whenever these two things come together, this code is executed on data being, so this code is executed on parameters passed in by this transaction which wants to consume this transaction output. Okay, I think, is that roughly clear? I think we will give some examples how this is being used in practice. But I think the idea of this conditional money transfer should become clearer now.
Yeah, so we don't have too much questions, only one regarding the validation of transactions. So are the transactions only verified by miners or also by full nodes? Or who verifies the correctness of transactions?
So every full nodes, so both full nodes and also light nodes would do it, because even if you read a blockchain, for example, you want to find out what's in the blockchain, you want to make sure that you not simply take the blockchain as it is, yeah, so you don't get download memory dump more or less of all the blocks, and then say, oh, it will be okay. But you would then run for each transaction in this blockchain the validation, yeah, that you are sure that the blockchain you received and the hash value for the blockchain you received is the correct one. And this doesn't take long. I think, Uli, you know it's minutes, I think, for the whole blockchain, even on a small computer.
To compute the complete blockchain.
Yeah.
Yeah, so currently for Bitcoin it's a little bit tough because it has 270 gigabytes, so that takes a little bit longer. So, but if I set it up on my local machine here on my computer, that takes 2-3 hours. That's not the issue. But on obviously on light clients or so, you don't do that, and then you can verify transactions. So one transaction verification takes less than a second.
So to summarize, also if you're not mining, if you don't want to add to the blockchain, but definitely the miners are the most interested in having a correct blockchain, because otherwise all the mining effort was wasted. But if you simply follow a blockchain also and you want to make sure that you really have a consistent blockchain, you do this validation. Once if you sync, and then every time you get a new block, you only have to validate this one new block, which doesn't take, it takes nanoseconds.
Yeah, exactly. Apart from that, we don't have any further questions I see now.
Okay, so therefore we now move on to this little programming language, and all little programming languages are called script, JavaScript, and often they start tiny and then they become monsters. In Bitcoin, this is not the case. Yeah, people sooner or later realize that it doesn't make sense to make Bitcoin a programmable system. Yeah, because of this transaction concept, it's rather tedious. So therefore, I think it's only conditions which you typically have in the very close vicinity of money transfer. It's only conditions you typically attach to money transfer. So therefore, I first will explain to you how this programming looks like, and then we talk about how do you use it in practice. Okay, so therefore in the previous slide we had this crazy string here of op dup op hash 160 op equal verify op checksig. Yeah, so this is obviously it's something which is called some people call it bytecode. Yeah, so these are codes, and some of the codes define operators on a stack machine, and others define operands which you push on the stack machine. Yeah, so therefore, this is a sequence of instructions and data values which you push on which you manipulate in a stack-based computer. So therefore, the transaction contains a script, and the scripting language is called Bitcoin script. And so therefore, you now have the identity is not a public key, but a hash of a public key. Yeah, so therefore. A person which wants to redeem the unspent transaction output needs to provide a public key that hashes to the public hash value for the public key, and a signature which belongs to this public key. Yeah? So therefore, we need to have a way to check if an entity is allowed to spend the transaction output. Yeah? So therefore, what does the script now do? In order to do this verification, it contains instructions to do the validation. Yeah? So therefore, the protocol is written more or less in the code. Simply like if you send somebody some data, and then you send it a function as a parameter, and then you ask the person to execute that function you've supplied with a certain value, and then you can validate whether the result, what your function computes, has the right result. Oops, what happened now? Sorry, I lost now the screen. Okay, so therefore we now execute the script. So therefore what we do, we take the script and we add to the script the values you supply, and then you run more or less the computer or the stack-based computer on the input which you supply by concatenation with the code. Let's look at this, what is happening here. So we now have here this code, check signature equal verify, then we have a value as an operand here, which we expect. Then we have an hash 160 opcode, and we have an opcode for duplicating, and then we concatenate the data provided by the signature key, which consists of the public key given by the person that wants to spend the money and the signature. Yeah. So that it's the person that you want to give the money to. Yeah? So they say essentially, it's me, give me the money. I'm authorized to get the money. So that's what the concatenation does. It simply takes this string here and concatenates this with a string, and then you start with an empty stack. Yeah. And now we walk through it line by line, and I do hope this animation is also in your handout. Yeah? So therefore, the box now explains every step. So in the first step, we have a program counter which goes to the signature, and therefore, if the interpreter finds a value, it pushes the value on the stack. So therefore, the stack now contains, after execution of this statement, the signature. Then we can move on to the next statement. Here, the program counter goes to the next statement. We have the public key. It's also pushed on the stack on top of the signature. So that's more or less the second operation. Then we have a third command, duplicate. It's a duplicate operation on the stack. As the name indicates, it duplicates the current top item on the stack. It takes the existing value here, it was the public key, it duplicates this public key. So therefore, we have now 2 copies of the public key that we can compute with. Then we have the hash operation, and the hash operation takes one operand of the stack, namely the public key, and produces one result. Yeah? So therefore, the value public key is consumed by the hash operation and replaced by the computation of the hash value to the operand, which is the key hash of the public key, the hash of the public key. Okay. So that's more or less the stack content, and now we move on to the third operation, where we push the expected value, which is written here, on top of the stack. Yeah, this is what you, as the author of this transaction, want to see. You say, is this now equal to the value I expect? So therefore, I push the value I expect here, and then I perform the equal verify operation, which more or less takes 2 values of the stack and compares them for equality. And if it's equal, the equal verify operation continues. It takes off these both values. It takes both values of the stack. Yeah, it checks whether the 2 top items on the stack are equal or not. If they are not equal, the program stops and an error is thrown. Now that's the basic idea. All these conditions essentially mean if these 100 conditions are satisfied, execute the transaction. So therefore, the only option what an operation can do is either succeed and go on to the next operation, or the operation fails and throws an exception. Let's say error appeared, and when an exception is executed, the precondition to the money transfer is not satisfied, and the money transfer doesn't take place. Yeah. So therefore, if these 2 are equal, we continue now with the next operation, check signature. Otherwise, the whole transaction fails and the money will not be transferred. Okay? And finally, we do a check signature operation. We now have the public key here and the signature, and then we verify that they are equal. Again, the check signature will then be verified. So the check signature pops the 2 items of stack and does the entire signature verification. If the signature verification is valid, then both items are consumed and true is pushed on the stack. The stack contains true and the transaction is valid. Yeah? So after execution of the script, we have a value here, either we crashed already, or we have the value true here, or we have another value here, then the transaction would also be failed. So now the question is, what's the expressive power of this programming language? It is not very expressiveness. So essentially, also what you don't want to have is anything which leads to loops. Yeah? Because if you would have loop statements, The jumps, where you could loop more or less and execute something in loop. You could simply send a program which loops as a script to all these Bitcoin nodes, and they would start running in endless loops. Or it would consume a lot of money and energy to compute very complicated things. So therefore, there's always this fine trade-off between a very expressive condition language and an efficiently computable and safe expression language. So again, the basic script codes are flow control. So do something if a condition is true. Do something if nothing is true, but you can only branch forward. You cannot branch backward. You have a stack control operation, like duplicate something on the stack, drop something from the stack, rotate elements on the stack. Then you have splicing operations, for example, to concatenate strings. Again, they are disabled. Again, maybe this was for security or space reasons. You have Bitcoin, bitwise logic, like AND or exclusive or negation operators. Again, they are disabled. Don't ask me why. Arithmetic operators. Again, you have addition and subtraction. Multiplication and division are disabled. There was a definition how they could be done, but the machines throw an exception if you want to multiply and divide. And then most importantly, you have built-in cryptographic operations for computing certain hash values of different hash sizes and also operations to do other cryptographic operations. One interesting point is you have a log time operation. So the idea is sometimes you want to say that you want to have time-dependent things. For example, you can rent an apartment, but you cannot leave. Like Hotel California. So you rent an apartment, but only you can leave after a certain time. Or if you you have to wait until you can spend your money. You get money, but you should only be able at a certain time to spend the money. So therefore, there are also operations where you can compare a certain value which is given with the current log time of the blockchain. So therefore, it's really of limited usage. So you have temporal constraint, you have identity constraints using the identities of the parties involved, and you have Boolean constraints on the values of your parameters. Okay, so any questions so far regarding the stack-based language programming scheme?
So we got some questions about, one person wrote, I feel like I got lost a bit, what is the signature in the transaction script? So maybe we can talk a little bit about what is the signature, what is the purpose of it, and what it signs, so that you get a little bit of an idea about that.
Yeah, so essentially, what's the idea of signatures? We covered this in the beginning, is this idea exactly. That like a notary, it's not enough to say this is the text, but it's essentially to say this text comes from somebody. So therefore, if you want to make sure that this is your, let's say, the amount comes from, so it's that if there says it's 5 Bitcoin, you want to make sure that this number 5 is not changed. So therefore, what you do, you take the value 5 and the other information, and you sign it. And so therefore, nobody, let's say no miner, no other party can change this value because it would make the signature invalid. The same thing is if you have a condition and you write the condition is that it doesn't do it between 12 o'clock. This condition is a piece of code. You have a script, more or less, and then you would write a signature below the script to make sure that this script is your script and not some fake script somebody invented. So therefore, the idea of signature is always to connect some piece of data, a piece of code, or a process description with some person who's the author of that information.
Yeah. Very good.
Okay.
That's exactly, yeah.
Okay. Thank you, Uli.
And let's continue, I think.
Okay, fine. Okay, so now we have this super duper language. How do we use it? And again, this is not so. this was a little bit Bitcoin specific, yeah. But it's, again, if you know programming is forth, in the old days, not people invented stack-based languages. Also, all interpreters for JavaScript and Java are stack-based. So that's the typical thing you do if you want to make something programmable. Yeah, you invent a language. Mostly it's a machine language like Bitcoin script. And this machine language is executed on a formally defined interpreter. And that gives you expressive power. And how this is done, that was specific for Bitcoin. But then if you now want to do money transfers, there are typical ways of authorizing people or groups of people to make decisions or to spend money. And therefore we show typical money transfer patterns. Yeah? Something like typical patterns of digital currencies, what we are now doing. Yeah, so that you more or less, it's like in the financial market, that you have certain ways how to restrict the usage of money. Okay, so it's patterns more or less. Yeah. So the first pattern, I think, which is covered in cryptography, are so-called multi-signature addresses. Yeah. So the idea is that you have an n out of m, for example, 2 out of 3 multi-signature address. It has then the following properties. It requires more than signature. It's not enough that one person says it's okay. It's not only signed, the contract is not signed by me, but also by my wife. Or the contract is signed by me and the notary. Now that's the basic idea. And then you could say, okay, it has. There are 3 authorized people, for example, Alice, Carol, and Bob. They could sign it. Yeah. But I would say they have the right to sign it. But each contract only has to be signed by 2 of them. Maybe you have an executive board of a company, and it's 3 executive directors, and they should have equal rights, but it should be always 2 people signing a contract to make sure that Alice doesn't do, or any of them does bad things, and another person has to sign it. Then you would use a 2 out of 3 signature scheme. And 2 out of 3 signature scheme is valid if the message is signed by 2 of these 3 people. Yeah, let's say either by Alice and Bob, or by Carol and Bob, or by Alice and Bob. And you can obviously go for play with this so that you have an n out of m signature scheme. Yeah, if you need. Okay, so clear. So where would we use something like this? So okay, here we would use it for authorizing money transfer if you have more or less shared wallets. Yeah, so that you have more or less money which belongs to the company, and you have a set of people which control the company. Yeah, that's a typical thing of having shared authority with multi-signature address. You can also use it in a so that's more or less on the sender side. Yeah, who can spend the money? Now you can also use it for a money transfer with unknown people, and this is then called the escrow accounts. Yeah, I think the escrow account is something very useful, and you know it from PayPal, for example. Yeah, let's say you want to buy something. Alice wants to buy some medication. I think she wants to buy medication for Bob on the web, and she wants to pay and is willing to pay money for that medication, yeah, to Bob. Yeah, that's the basic idea. Now maybe the medication is very expensive. Yeah, let's say $5,000 or 1 Bitcoin. Then Alice would be hesitant to first give the money to Bob. Vice versa, Bob would not be very happy to give the medication to Alice before he or she received the money. Yeah, that's more or less a deadlock situation. And therefore, if you have very complicated contracts, like you want to buy a house or you buy a car or whatever, that is very typical to have an escrow agent in the middle, so that both parties more or less, and both parties have to trust this escrow agent. Yeah? This has to be a trusted party, like for example PayPal or bank or notary. Sorry, get a call. So that would be the typical way that Bob now, let's say, start with Alice. She gives, in the first phase, Alice gives money to the escrow agent. Bob gives the medication to the escrow agent. And then the escrow agent validates that he or she has both, and the medication has the right properties Alice demands, and that the amount of Alice is the right one which is demanded by Bob. So therefore, the escrow agent is the central figure here in this area. And obviously, in the Bitcoin blockchain, you cannot send pills, but maybe this would be a secret, an iTunes song, or a key to unlock an iTunes song, or that would be a key to unlock a door to a very smart, big apartment, which is very expensive, or it would be a patent. So therefore, Alice gets the patent only if she pays the money. It could be something digital here, which has value in the real world, a digital asset. And only if they fit, the escrow agent then does the value exchange. Money against a service or against the product. If anything goes wrong, the escrow agent would say, "Oh, sorry, this was not true," gives the money back to Alice and the money back to Bob. And obviously, you would pay a little bit money to the escrow agent, or very much money in Germany for the lottery for your house, and he simply is paid for having this trust. Okay, so that would be a traditional escrow. And obviously, we want to get rid of this trusted party in Bitcoin. So therefore, what we would do is, so therefore, Alice would now create a 2 out of 3 multi-signature address and transfers the money to it. So the idea is, so she says, it's not enough that Bob, so it's not enough that Bob is here. There have to be 2 signatures present. So therefore, this 2 out of 3 signature would define that there are 3 parties, Alice and Bob. These are the 2 parties of the contract, and the third signature of an escrow identity, which is virtual. It's a virtual identity which can also sign. Let's look at it. So therefore, Alice would say, "Okay, I'm happy. Here's the money, but I put it on the table. But the money on the table is locked now by the condition that 2 out of 3 people, let's say Alice and Bob, or Alice and the escrow agent, or Bob and the escrow agent, have signed it, and because then they can unlock the money. That's the basic idea here by using this 2 out of 3 signature wallet. And once and then since now the money is on the table, so Bob sees the money here. There's real money here. He would be willing, because Alice cannot withdraw it anymore. He would be willing to give the product to Alice. And once Alice receives the product, she would sign the contract. Bob would sign the contract. Bob would sign the contract. Alice would sign the contract, and then the money is released, and Bob gets access to the money. Okay. So that's the basic idea. That's the idea here. So that's the positive case. Now you would say, what happens now if anything goes wrong here? And if anything goes wrong, Alice would. So maybe, but what could go wrong? There are 2 things that could go wrong. Alice puts the money here, and Bob never sends something back. So therefore, after a certain point in time, Bob would not sign it, and then Alice would more or less activate the escrow account or take on the escrow role and would sign it to get the money back to her. She would redirect the money she put on the table back into her own pocket. And that's more or less the idea, that either this atomically happens, that she gets her money back, or she gets the money back and she gets also the digital goods of Bob. Okay. I think that's the basic idea, that you now can lock money visibly on the blockchain, because everybody can look at the blockchain that the money is there. And now only a limited set of people can get access to this money. And that's the basic idea of this escrow. The typical disadvantage of escrow systems is here that the money, if Bob now waits very long, let's say 5 days, 7 days, 10 days, etc., the whole time money now has, the money is locked here. So therefore, it has to be real money. It's not just the option of to get money, and it also the time it has to be locked is, let's say, depending on how long Alice is willing to wait for the answer of Bob. Yeah. Yeah.
So we got some questions about the escrow, and I think these are very good questions. First of all, is the escrow agent a physical person or a script? One person can scam the other if the escrow agent has an agreement with one of the two parties. And
no, it's not a physical person. It's a virtual.
Yeah. So the point of this of the slide is to show you that there's an option to enhance the traditional escrow with Bitcoin, for example. So the problem that people mention in the questions in terms of, okay, the escrow, is it a virtual person? Is it a real person? Is it somehow can we buy this person in terms of that it plays along with our side? These issues exist both in the traditional escrow system and in the Bitcoin escrow system. The advantage of the Bitcoin escrow is that we actually do not need an active involvement in the escrow if both parties behave correctly. And in a traditional escrow, the escrow has always to be present, has always to exchange the goods and the money. So that's the main point here to make this difference.
Yeah, he's not the escrow. He's the arbitrator in the end. Yeah, only if anything goes wrong, the escrow would now have to determine what happened. Did the good arrive? Yeah. So this is typically what's happening often, that you do the bookkeeping here and it's totally automatic without the escrow agent. So therefore it's not expensive, because if both sides behave well, and if you look at the behavior of people in social networks, so there's, if they know, so they all behave well. Yeah, so the typical eBay users, despite what everybody assumed, are behaving well. Yeah, because they don't want to spend time with illegal transactions, etc. Yeah, so therefore, in 99.9% of the cases, this work runs through. Yeah, because Alice puts it here, and the trust is in the network that the money is here, and then Bob can validate it. And only in case that the physical good doesn't arrive, which is not possible to be checked on the blockchain, you would involve an escrow agent, which in the real world would more or less like a notary or like a arbitrator or like a trusted state agency or court would then start looking at the transactions here and say, okay, there's obviously something going wrong. Alice put the money here, and the money is locked here, and Bob didn't fulfill it, and then the escrow agent would decide what went wrong. Now, did Bob not send it, or did he send it? And Alice more or less claims to not have received it. That would be the typical goods here in real life. Okay.
Very good.
So then we.
So to clarify one last question on slide 25. So this multi-signature wallet transaction in step 3, Bitcoin escrow step 3, is it signed by both parties or by one party?
It has to be signed by both parties, A and B.
Yeah, exactly. So
here.
So people one question was, what would stop Bob from signing this multi-signature party, this multi-signature wallet, without sending the goods or the medication? The answer is Alice would not sign this multi-signature transaction as long as she did not receive the goods. So that's the important part here.
Yeah.
Okay, I think we can continue.
Okay. Another use of Bitcoin script would be micropayments. I think the vision, so I think the vision of digital money was always that you can now spend very tiny amounts of money. In reality, this didn't materialize up to now because the transaction expenses let's say, of paying, let's say, 0.0 cent for once playing an iTunes tune are too low. So therefore, you typically have something like subscriptions, yeah, that you bundle. You say, okay, you get to Spotify and you pay per month €9, and you have arbitrary many songs, yeah, so that you get in, because the money transfer from you to Spotify is so expensive that if you pay per tune, that would not be possible. Or if you pay per click, etc., for advertising. So these are these ideas of micro or nano payments that you have very tiny amounts of money which you transfer. Also, what we do here with Bitcoin is not really realistic. You wouldn't do nano payments or click payments with Bitcoin network, because also transaction fees, and in particular transaction time of Bitcoin transactions, take long. Yeah? So therefore here you shouldn't think about things like pay per click, pay per sound minute, or whatever, or pay per kilometer, but it would be something where you have larger amounts of money, like annual subscription of some software, and you want to pay it monthly, yeah, or you have, so there where we have reasonable amounts of data, yes, money. So therefore, it's recurrent payment and not so much micropayments would be the best title here. But this is only due to the limitations of the cost and speed of the Bitcoin network. We could use now this scheme, and therefore we talk about digital money transfer schemes, which we would also use in Ethereum later on, or in permission blockchains. This would be a typical viable product also for micropayments, where you more or less have very small transactions and with tiny value. And what's now the idea with these multi-signatures here? So let's read it carefully, because it's easiest before I only point to the screen. So the idea is now we have something like a subscription. So Alice wants to continuously use a service from Bob and pay, let's say, reading a blog, viewing YouTube videos, whatever, from Bob, and pay a certain small amount of Bitcoin for each usage. Usage pay as you go. Or software as a service, for example. So therefore, if you would create now new transactions every time, wouldn't work, because too many transactions would be created, yeah, and therefore the fees for the transactions would be too high. Yeah? So therefore, one potential approach would be that at the beginning, Alice sends her maximum spendable amount to a 2 multi-signature address. Yeah, so therefore you would essentially say, okay, I'm willing to pay, let's say, my Trello license or my conference license for 1 year. This is I'm willing. So therefore I spend, for example, 12-month payment for Trello. So that would be here 10 Bitcoin for to an account offered to Bob. And then the idea would be that every time she consumes the service by Bob, she signs a transaction locally for the multi-sig address, sending the accumulated amount to Bob and the charge changed to herself. A message containing this complete transaction is sent to Bob. Yeah. So the idea would be now that Alice now fills out a transaction and says, okay, the first time you get now. I filled out the signature that you get, let's say, we want to do 10 times, I think. For example, we would spend in the first time 1 Bitcoin, and she would say, okay, I'm willing now to spend 1 Bitcoin to BEP, but I don't want this transaction to be executed because the transaction fee would be too high. I simply show that I'm willing to do this. Yeah, that's the idea here, that she signs now the transaction locally on her machine and sends it to the network. The network, again, sees that it's an incomplete transaction, so therefore sooner or later this incomplete transaction reaches Bob, who has now the certainty that this transaction is here, and if he wished to, he could sign it and get the money immediately. Yeah, so therefore Bob could be greedy and say, no, I want to get it, or he would be patient and say, yeah, I know here's the money, and if I don't grab now the money, I don't have to pay the transaction fee. So therefore, looking at this amount and seeing that Alice now committed this, he has the security that he in the end will get at least one of these 10 Bitcoins, but he wouldn't now get it. Yeah? He would simply wait for the next transaction from Alice to come. So therefore, after then there would be a second transaction that Alice now says, now I'm willing to give 2 bitcoins. Bob says, aha, 2 bitcoins. She gets now the service for 2 bitcoins, but he doesn't spend the money. Yeah, he simply leaves it here. So therefore, no transaction has to be propagated in the network. No transaction fee occurs. Yeah, so therefore, the Bitcoin network is now used as a message channel for these 2 parties, which are now informed about their goodwill. And this, here the locked the multi-signature account gives Bob the security that whenever he wants to get the money. Okay, so if now Alice is finished using the services, so if she now consumed all of the coins, Bob would sign the multi-signature account and would get his 10 coins. Yeah, that would be more or less the expected progress, what could happen here. Is that clear? What's the idea here? Okay. Okay, so then there's, then there's a problem. Maybe somebody already read in the script and can say what's the problem or what could go wrong. Okay, so no comments.
So one idea was if she doesn't spend all the money, Bob has to sign the transaction to send the rest back to Alice. Bob could sign any of the old incomplete transactions to receive additional money. And
Okay.
another idea is double spending.
Yeah, so I think the first proposal was, okay, there are now a lot of transactions floating around from Alice. Yeah, she signs, yeah, you get 1 coin, you get 2 coins, yeah. And why wouldn't Bob now try to spend all of them instead waiting for the last one? I think, did I correctly understand the first question?
So I think the first one is that when there are multiple transactions, you can spend all of them or many of them and receive additional funds.
Exactly. If this, but that would be a false assumption because you could try it, you would do it the first time, but then the network would find this out, that this was already spent, the output. Yeah, you remember each output can only spend once, so therefore you would now have transactions where the same, where you spend, where Alice spends more money than is on this account.
Exactly. So you can only spend money that has not been spent previously. In that second, Bob decides to spend one of Alice's pre-signed transactions, then all the others become instantly invalid. So that's not an issue here. Another approach is,
and it also could,
yeah.
Yeah.
Another,
and that's the same. Yeah. Okay.
Continue, Florian.
Yeah, and that's the basic idea. I think the Bitcoin network has to make sure if different parties of Alice sends in different nodes in the network the same, I spend the money here and I spend the money here. This is the core problem of Bitcoin. Yeah, to make sure that if Anna sends out money at once through different nodes and tries to more or less confuse the network, that's the core consensus protocol. That these inconsistent states are detected with 100% certainty and rejected. And that's double spending attacks. And we will talk about this, how this is reached in the consensus protocol.
How this is evaded. So exactly double spending should be prevented here. So no further posts on Tweetback about about the problem. But I think Florian, you can take it further.
Yeah, and again, this is a typical problem, but one doesn't think about. It also happens to me if I do contracts, that I always think Bob will do something. Yeah, if there's a more or less, how would you call it, eine Verpflichtung, obligation for Bob to do something. Yeah, because now Alice puts that money here, she doesn't own it anymore, and if Bob would never take the money back, and he wouldn't also give anything here, this 10 bitcoins would be locked here in this account and Bob would never appear. Yeah, so Alice would essentially have not given anything. Bob wouldn't earn something. Bob would simply do harm to Alice because Alice, now poor Alice, has 10 bitcoins locked in this multi-signature account where she can no longer get access to it. And that's the reason why So that's the idea. The problem is that Bob could decide not to sign the last transaction or any transaction at all, leaving Alice stuck inside the multi-signature address. So therefore, the idea is now that we need now this idea of lock time. So the lock time essentially is saying, okay, if you want to enforce something to happen, you always have to give people a deadline. So therefore, if we say students have to register back for the new semester, this is not enough. Because maybe 5 years later, we will say, I want to register for the next semester. So therefore, you always have deadline if there are obligations. If there's an obligation to pay money, it's always saying you have a Zahlungsziel in German, you have a time when you have to spend it. So therefore, we now understand why it's important to talk about timing, that we say you have to do something, you have an obligation, and this essentially means you have a certain right which expires if the time goes out. So you can do something to a certain point in time, but this right expires after a certain point in time. And this then effectively turns a right into an obligation. So in order to ensure that Alice receives her money back, she can demand from Bob to create a transaction from the multi-signature address, transfer the complete funds back to Alice before creating it. So therefore the idea is now Bob creates a right for Alice to get the money, and rights are easily enforceable. So therefore Alice has now the pending right to transfer the money back to herself. But only the transaction contains the lock time, as the transaction should only be spendable after a certain amount of time t, and if the output is not spent otherwise. So therefore, the idea is that's more or less this time lock, that Alice can demand now the money back if Bob doesn't in time take the money. Okay. So therefore, with this additional protocol step, so we now have a more complicated pattern. Alice does something, then she asks Bob to do something, and then only if Bob does this, she does that. That is rather a complicated protocol, but which ensures more or less that she will get her money back. Okay. Okay. So a final thing is what you also can do is a proof of burn. So that you use more or less Bitcoin script to show that you own some Bitcoins and you destroyed them. That might be helpful, for example, if you want to exchange Bitcoins in one system, Bitcoins into other digital currencies in another system. Or you have another Bitcoin system, so burning money makes sense if so burning money in one system makes sense if other values are created either in the same system, like something is computed, whatever, in Ethereum, or like in Bitcoin, you want to prove that you don't own the money anymore. So there's more or less this bootstrapping for other blockchain systems, that you want to destroy money here. Potentially, I think there might be also scenarios if there's evolution or if you have rights associated with Bitcoins, that you more or less want to make sure that you give up these rights. Okay, so that would be this op-return operation, which more or less throws an error, and so therefore it leads to the fact that the money will not be. It will be consumed but not spent. And finally, there's the opportunity that you use the Bitcoin blockchain to store data. Remember we had this data block in the Genesis block, which contained the headline of the New York Times, or you want to store URLs in the Bitcoin blockchain, then you can use essentially arbitrary data, here. And before the data, you have an op-return code which returns the execution of the transaction. So therefore, you use the Bitcoin blockchain as an information storage. That you store information there which is visible to everybody on the planet. Okay. Okay. So that's more or less the point. Now we have a slight complication. Maybe it takes longer than 4 minutes. So we have a little bit of a complication. So if you want to access a certain address, you have to know whether it's a normal address or whether it's a multi-signature address with 2 signatures, or whether it's a 3-signature address and you have to supply 3 signatures. So therefore, if you have a certain transaction which have a certain code, some of these transactions require 2 parameters, other might require 3 parameters, or only 1 parameter. So therefore, this matching that you now as a consumer of information have to know what's the protection scheme of the people, of the money you want to spend, which might be inconvenient. So the data provided by transaction input has to match the parameters expected by the transaction out script. So therefore, if you have now a wallet of a company and you want to pay for some goods at the company, it might be the case that you get the money directly, or that it requires now the signature of one of the CEOs. And then you not only have to provide your own signature, but also you have to wait for the signature also of the CEOs. And that's more or less the problem here, that this would be inconvenient, because you have to know the origin of your money. It's not only Bitcoin you want to get, but it's Bitcoin with some conditions and some parameters, and you also have to know what you have to do here. So that would be the real world example here, that you want to now get your money you want to pay with Bitcoin. So therefore you want to store all their money. It was the other way around. So you want to store money, you want to give money to a company, but the company wants to make sure that the account where you put the money is 2 out of 2 multi-signature account. So therefore, you now have to know, if you create the money, that this is money that will be should be 2 of 2 multi-signature money, so that later on, if this money should be spent by the company, 2 CFOs have to sign it. And that's the disadvantage. So normally you want to say, I couldn't care less what is their signature rule, because I give them my money, and they shouldn't bother me with their complicated signatures here. And based on this, the idea is now, this is not user-friendly, as most users are not aware how to create a transaction with a certain script. This is because the sender has to define the script. So therefore, you as a sender have now to define the script that is expected by them. In order to avoid this, and this is described here. So that's more or less the script that allows to spend the money is now created by you, but again, it limits how the company can spend the money. So therefore, the company essentially wants you to do something in favor of them. And to turn this around, this is called pay to script hash, is that you now write a script that computes the hash of transaction in and checks it if it's equal to the predefined hash. So therefore, this is more or less that you pay now to a hash value. You say that there's a script which I don't care what it is, but I now simply sign that I'm okay that this script is executed later on in my money that I spent here, but I don't have to care for the other parameters here. That's again the trick here, and this is typical things that I think normal people wouldn't think about, but if you are from the cryptographic world, this is the nice idea that you more or less with hash values, you more or less can commit to something which you don't care about, and later on you can verify that the real script has been used here. And to summarize here, and maybe then you can digest it and ask questions next week. So therefore, the main advantage is it shifts responsibility from the sender to the receiver, because the receiver can define the script and compute a hash value for it, and you as a sender don't have to copy the script into your code here. And the receiver gives a hash to the sender. The receiver has to make sure that it has a script and that hashes to the hash. And this also leads to an efficiency gain. I think it's of minor importance, but it also happens in Bitcoin, because if you would write a lot of scripts into these transactions, the transactions get larger and larger transactions are, so if you have short transactions, more transactions can be packed into a block, and therefore short transactions are preferred by the miners. Yeah, so therefore, if you have a short script here, it's preferable. Okay, I think that should be enough for today. And again, you can see how with a little, very small, tiny set of instructions, we can add a lot of expressive power to our digital currency. So therefore, we stopped, I think it was page 23, I scroll down, that we talked about, let's say, how it's represented, how transactions are verified, what is the expressive power of the Bitcoin script language, and then we talked about use cases. Yeah, what kind of conditions can you formulate? And then we found out essentially it's conditions based on the owners or the authority of the people. Yeah, using multiple signatures to make sure that more than one person agrees on the transaction. We also had time-based constraints. Yeah, so that maybe only certain, after a certain time, after a lock time, a transaction is valid. And also you can imagine other conditions based on, let's say the receiver, the amount, etc., which you could formulate, but which are not that prevalent in practice. So therefore, we talked first about the multi-signature addresses and how they can be used to realize escrow accounts, which only in the case of non-conformance require an escrow agent externally to look at it and resolve the truth, what happened with the value transfer in reality. The second use case was micropayments, where Alice and Bob want to pay to a longer-term contract, which consists of individual transactions, like a subscription of news or a subscription for some other service with micropayments. And in order to not to have too many transactions to be validated, that this, again, we had this pattern of a multi-signature solution, which allows more or less Alice and Bob both to cancel more or less a subscription and making also sure that Alice can get her money back, which she put onto a deposit account to more or less protect the whole transactions or the whole series of actions. We had also the lock time, and then we also talked about burning from bitcoins. Yeah, that we have a return operator, which more or less throws an error, and which at the same time also transfers money. So which allows more or less to burn currencies without transferring them to a destination. And then we have one problem I think we started to discuss about, and I want to finish with this section today. It's only 2 slides. But I think the important point is, you remember, maybe I go back to this picture. Yeah. So we have this so if you have one transaction, it has these inputs and it has these outputs. And these outputs become the inputs of future transactions. And now the interesting question is, if you now attach a script code to the output and to the input, who at which time creates the output and the input? And unfortunately, it's the case that once you create money, so if, for example, this is a bank, and the bank wants their money to be protected, that only with 2 signatures the money can be spent, it's important for them, more or less, that people create certain unspent output with conditions, so that if you are a customer and give money to the bank, you as the customer would be required to create this output in a format that it requires 2 multi-part signatures to be presented. And since this is not the case, what you want to achieve, there is now a way, which we are talking now on page 29, how you can turn this around. Yeah? So the idea is now, we have this real-world example of script compatibility, that you as a customer want to give money to a bank. The bank has the goal to use 2 out of 2 multi-signatures, that if the money of the bank should be spent, it should be protected by this 2 out of 2 multi-signature script. Unfortunately, you are creating this script, and therefore this is more or less a challenge here. Yeah. So therefore, you don't want to know what kind of rules they have for spending their money. You simply want to give them the money. So therefore, the idea is now that you want now to turn the responsibilities around with the script. So to remember this perspective, now you want to make sure that the transaction 2 to spend the money, which will later on spend the money, has to be signed by both CFOs. Yeah? So therefore, you want to And therefore, the rule where the location where based on the Bitcoin protocol this script has to be located is in your unspent transaction output. Yeah, and that's unfortunate, yeah, because while you're getting the money, you don't know whether you want to spend it later on for that company. So therefore, the idea is to solve it around that you essentially say that so that you now write a script on the transaction outside that you say, I don't want to define the script. I want to simply make sure that if I give money to this transaction can prove the consistency of the script they are having. Yeah. So therefore, the idea is that you now move the script from the left-hand side to the right-hand side, and you simply demand that the hash value of the script is the one you would expect. Yeah. So therefore, the bank essentially can keep their code, what their policy is secret, but they simply have to reveal the hash value of this code which they will be providing, so that you can be sure so both parties can be sure that these two things match to each other. Yeah. So and this is then called pay to hash script to script hash. Yeah. So I pay money to a script hash. Yeah. So I don't pay to a certain script, but I pay to a certain script hash. So therefore, the message essentially saying send money to the hash of a script. Any script which has this hash value does the work, but since we use cryptographic hashes, it's essentially the one script the bank chose. As I already said, it shifts the responsibility from the sender to the receiver, as the receiver gives the hash to the sender. The receiver has to make sure that it has a script that hashes to the hash. So the sender doesn't have to know the details of the script, it simply has to know the immutability and the unchangeability of the script. Another reason why you want to do this is an efficiency gain, because you don't have to store the whole script here, but you only have to store the script hashes. Yeah, and so therefore, because miners have to store all unspent transaction outputs, in the mining pool, you have all unspent transaction outputs because they only can be spent, and they get much smaller if they only contain a much smaller script instead of a lot of repeated similar scripts which always serve the same purpose. But again, that's not the main reason. I think more importantly in practice is the first argument. Okay, that was the last example of more or less also inverting more or less responsibility with script hashes. And again, it's a principle you could use also in other scenarios. Maybe while I'm switching, Uli, there might be some questions. By the way, there's one question I forgot to address. We got questions regarding the format of the exam. And there's an ongoing discussion at the faculty level and at the university level and also at the state level. I think currently, the general idea also from the student representatives, from the professors and the VMEs is that I think the best way to preserve the quality of the exams and to have a very predictable way of the exams is to have exams physical exams where we have very, very, very large rooms, where there's a safety distance between all the students and all the supervisors, so that we maybe don't find a lot of these rooms at the campus, and maybe we have to move off campus to maybe the trade fair area which is currently unused. There are discussions ongoing, who pays for that, how we organize it. It also happens now for the repetition exams of the last semester, so therefore we don't have firm information about what is possible for blockchain-based software engineering and CIBA master. But for the smaller exams, it should be easy to do it at the faculty or at TUM, and maybe with blockchain-based system engineering, we have to find other location. But up to now, we don't know what will happen, or if maybe we even have to go for an online exam.
Yeah.
So please hang on, but it will be this semester, there will be exams.
So we got two questions on TweetBack. The first one is, What if there is a copy-paste error in the script hash when creating the pay-to-script hash transaction? Would the receiver still be able to access the money somehow?
No, as usual, if you do not only, whenever you send money to an account which maybe doesn't exist, the money is lost. Yeah, so that's the problem you have. Yeah, unlike if you do a bank transfer and you use the wrong IBAN number, the money returns to you back and you have to correct it. Unfortunately, in Bitcoin, the money is definitely lost.
Yeah.
Because for years, even if you know the number you entered, it would be very, very difficult without a quantum computer to create a wallet which matches the wrong ID. Or even worse, this account has already been taken and somebody else could take it. Yeah? But they wouldn't be notified about it. So they would be notified that your money arrives on their account, and maybe you could try, I don't know how you could contact them even. So essentially, you have to be very, very sure if you use blockchain-based systems to use the correct target addresses, because otherwise the money evaporates.
Yeah. A further question regarding pay-to-script hash. If it has to be executed and enforced by the whole network, how can the script stay private?
How can the script stay private? No, they are not. So in this sense, they are not private. Yeah? So it would not be clear from the outset that this is a script which belongs to, let's say, the Deutsche Bank. Yeah? So you would have to execute the script. Yeah? It's like if you have a cloud computer and you execute some very secret computation on the cloud computer, then this would be visible more or less, yeah, because at some point in time the script has to be executed, it has to be decrypted, because you have to execute the script and not the hash. You not only verify the hash. So therefore, in this sense, the script is not a secret of the bank. Yeah, it would be accessible to the miners, but again, they would have to do some engineering to find out that this wallet ID belongs to the bank.
Yeah, so in theory, the script stays private until you actually spend the money, and then you have to publish the script, and then it's becoming public. Okay, last question for pay-to-script hash.
But again, it would be important. Let's say, for example, in the use case we had, yeah. So we want to make sure that the receiver wants to make sure, or essentially, normally, if, for example, if you get a contract signed from the technical university or from a GmbH, you should be better know if the people are allowed to sign the whole thing. Yeah. So therefore, even if you get, let's say, an order, let's say, imagine you get an order from a company, you have to be sure that it's not some, let's say, practicant or some secretary signing the whole thing. It has to be signed by the legal representatives of the company. So in a sense, I think therefore also it's important for the receiver of whatever here is being done that both CFOs signed it. Yeah, in this sense, even they might want to know it, that the company reveals that these are that this is the signature policy of the bank. Okay.
Yeah. Last question for pay-to-script hash. When using pay-to-script hash, how can the signatures which secure the transaction using the pay-to-script hash output as an input be included?
How?
So the question is basically we provide a script. So the pay-to-script hash secures a script.
Okay. Mm-hmm.
And how do we provide parameters for this script?
Exactly. So the idea would be, so now the first step is down. So this transaction is created by you, yeah, as a customer. You say, I want to give my money to my bank. Yeah. So there you would create this. And then there would be the validation script, which has, and then the CFOs want to, so the CFOs both want to create this transaction. So therefore they have to sign this piece here. Yeah? They have to sign, at runtime, they have to give them two parameters, which run through the 2 out of 2 signature script, which then takes the amount which is protected here, yeah, with the condition that this script has to be the script that has been published by the bank. So therefore, here's the validation done with your input and your hash value, with this script, and then once they want, at a data point in time, they provide the two signatures, and then they spend it to provide the money to other people. Yeah? So there's this dynamic binding through the parameters of the script at spending time, so that the signatures are provided. So the CFOs don't have to sign that you give them money. You have to sign that you give them money. So your condition is here, and their condition is then here. Okay?
Okay. So I think there are no further questions on TweetBack. So I think we can continue with the next slide.
Okay, but I think to summarize, this is the interesting point. Yeah, you have functions more or less as first-class values in these languages, these higher-order languages. So therefore, you could do very nice things with these. That you have, you could even imagine what is not being done here, but in Ethereum, that you pass around functions or references to objects which contain functions, which more or less allow you, let's say, like you know it in object-oriented programming, inversion of control, etc. Yeah, and the same things happen here on these very materialized chains of code, data, and arguments, which are then passed later onto code. Yeah, so therefore, even if it looks a little bit intrigued what we're doing here, it gives you an idea how powerful these blockchain-based systems are, because they both combine in a consistently preserving way data and code. Yeah, they're not only databases, but they are databases with execution engines for rather